Well, constant pressure calorimetry. We talked about constant volume calorimetry. This is constant pressure. This is much simpler to actually do, and we're going to do it in lab on Thursday. So here is what we call a coffee cup calorimeter, because it's literally made out of 2 coffee cups, 2 styrofoam coffee cups. Why do we use styrofoam coffee cups? It's a good insulator, right? It's cheap. You get your coffee in there, and you don't need a sleeve or anything on it because it insulates and it doesn't burn your fingers. So we're going to use 2 of them to just get even more insulating power. We're going to put a lid on here, but it's going to be a loose-fitting lid. We're actually just going to use crummy old pieces of cardboard. We don't have fancy cork lids. But that helps to keep heat from leaving through the top of the cup. It needs to be loose, though, because we want constant pressure, right? We want the pressure inside to be the same as the pressure outside, no pressure changes. So constant pressure, we're going to apply Q equals MC delta T to the solution. So we're going to have some water in here, perhaps, or we're just looking at the temperature of the solution in which the reaction is occurring. That's going to be the mass of the solution times the specific heat capacity of the solution times the change in temperature. The heat for the reaction, whatever chemical reaction is occurring, is going to be the same number as the heat of the solution, but the sign is different. Okay? And going back to what we talked about earlier, the heat of reaction is Q at constant pressure. So that's a Q reaction for this type of experiment. If we want heat of reaction per mole, then we just divide Q by the number of moles that gave that amount of heat. Any questions? Let's look at an example. The addition of hydrochloric acid to a silver nitrate solution precipitates silver chloride according to the reaction given there. When 50 milliliters of 0.100 molar silver nitrate is combined with 50.0 milliliters of 0.100 molar hydrochloric acid in a coffee cup calorimeter, the temperature changes from 23.40 degrees Celsius to 24.21 degrees Celsius. Calculate the heat of reaction for the reaction as written. Use 1.00 grams per milliliter as the density of the solution and specific heat capacity of 4.18 joules per gram degree Celsius for the calculation, the specific heat. Okay? So what we have here in this coffee cup calorimeter is we've got Q reaction is equal to negative Q for the calorimeter. Actually, let's call it the solution. It doesn't matter what side you put the negative on. It's just they're opposite in sign. We want to calculate Q reaction because at constant pressure, that's equal to the heat of reaction. So what we'll do is we'll calculate Q solution and then slap a negative on it, change the sign. So Q solution equals MC delta T. The mass of the solution times the specific heat capacity of the solution times the change in temperature of the solution. Well, change in temperature is easy to calculate. Delta T, I'm going to run out of room, so I'm sticking things in funny places. Final minus initial. So 24.21 degrees Celsius minus initial 23.40 degrees Celsius. And I think that comes out to 0.81. Check my math. How do we find the mass of the solution?
Can we do the milliliters the moles, which will, or molarity, which will give us the moles, and then convert the moles to grams?
Well, we could take the volumes and the molarities and find the moles of silver nitrate and moles of HCl, but that's going to give us the mass of the solutes. We want the mass of the whole solution. There's water in there. So weigh it, right? Why not? Well, we can't weigh it because it's on paper. There's information in here that allows us to calculate it. Why did they give us the density? If we know the volume and the density, we can calculate the mass. So what is the volume?
It'd be 100 milliliters.
It's 100 milliliters. 50 of this and 50 of that. So you add those together, right? I'm just going to get rid of this title. So 50 plus 50 equals 100.0 milliliters. Then if I multiply by the density, grams with milliliters in the bottom, so those cancel out, it's 100.0 grams. That includes the solution, the solvent and the solute. So there's my mass. I've got mass, I've got delta T, and I've got specific heat capacity. So I can calculate Q for my solution. So Q solution equals the mass, 100.0 grams, times the specific heat capacity, 4.18 joules per gram degrees Celsius, times the change in temperature, 0.81 degrees Celsius. And I look at my units, and the grams and the degrees Celsius cancel out. So I know my unit's going to be joules. 100 times 4.18 times 0.81. So 338.58 joules. How many sig figs? 2. This temperature change only had 2 significant figures. So that's Q solution. If I want Q reaction, I need to change the sign. So it's going to be negative 338. I'm not really done yet, so I'm just going to bring those guys along. And then we think about this. Okay, delta H is negative. It's an exothermic reaction. It's releasing heat. Yeah, that's why the solution temperature went up, because the reaction released the heat. But it wants delta H for the reaction as written. Well, how many moles of silver nitrate are written in the equation? 1. How many moles of silver nitrate did I use in the actual experiment?
Well, isn't it just, that's the 50?
Now we need to use the molarity and the volume.
Or 0.05?
0.05. So we've got 50.0 milliliters, which if you put that into liters is 0.0500 liters, times 0.100 moles per liter. 0.005. Yeah, you know those pesky little zeros. So our actual experiment, we were using this many moles of silver nitrate. How many moles of HCl were we using?
Just the same.
It's the same, right? The same volume, the same concentration. So it's going to be the same number of moles.
How come we don't just use the one, like going into the reaction where there's 1 mole involved in the silver nitrate and the HCl?
You mean like a mole ratio?
Yeah, the mole ratio.
Well, if you look at a mole ratio, then you would see how many moles of this you need to react with 0.005 moles. But did you actually have them? Yeah, we did. So this is a rare situation where we have just the right number of moles of each reactant. You could have a situation where, in fact, you often have a situation where one of these is a limiting reactant and the other is in excess. So then you'd want to look at the one that's the limiting reactant, because that limits how much of the reaction can occur.
So then we do our heat from the reaction divided by the moles.
Yeah, so we want to find out for 1 mole, how many? Well, this was negative 338.58 joules when 0.00500 moles reacted, right? And in our reaction, we actually have 1 mole, so then multiplying by 1 mole. So 338.58 divided by 0.005. I'm getting 67716 joules when 1 mole reacts. And how many sig figs? 2. What might be a better unit than joules? Kilojoules. So if we move the decimal point 3 places over here, then we've got minus 67.716 kilojoules, or negative 68 kilojoules. So we could write this up here, as is often done. Delta H for the reaction equals negative 68 kilojoules. Any questions?
Where did you get that 1 mole? We were just trying to get rid of
The 1 mole here I got from there being 1 mole in the reaction. If this was 4, like in the previous reaction, it was 4 moles, then I'd have to multiply this by 4.
Okay, so the bottom
Whatever the coefficient is, this is the number of moles that were actually used in the experiment. This is the amount of energy actually transferred in the experiment. We get that in joules per mole. Then we're going to scale it up to match the chemical equation. Yes?
So do you go off of the one that's a limiting reactant?
Yeah, if there are 2 and they're not stoichiometric, then you would use the one that's the limiting reactant. Because what will happen to the excess is it'll just sit there, it won't react. Any other questions?